Hello and welcome back to my channel and part 2 of my discussion on dome ports. If you haven't seen part 1, episode 3, I highly recommend that you watch that one first by clicking on this link here. In the first part of our dome port discussion, we saw how dome ports can eliminate the color dispersion that plagues flat ports. You may have gotten the impression that a well-placed dome port solves all our optical problems when we take photos or video underwater. Unfortunately, this is not true. As flat ports are plagued by color dispersion, dome ports also have a problem all of their own. The dreaded field curvature. Because the water outside of the dome is shaped by that dome into a concave shape, it acts like a negative lens. This negative lens bends parallel light rays from infinity outward, like this, producing a virtual image of infinity here, at a distance 4 times the radius of the dome, from the center of curvature. Because of this, your lens must focus much closer than the actual distance your subject is at. But this also works at an angle. At the edge of your frame, infinity will appear to be at 4 times the radius from the center of curvature, which puts it here. So you can see that the dome port creates a virtual image of infinity that is curved around the center of curvature of the dome port at a distance of 4 times the radius of the dome. What about objects closer to the dome? If we use a dome port with a radius of 10 centimeters, infinity will appear to be at 40 centimeters from the center of curvature. And objects that are at 1 meter distance will appear to be here at a distance of 32.5 centimeters from the center of curvature. Most lenses are designed to focus on a flat plane. When you focus on a wall at right angles to that wall, you want that wall to be in focus both in the center and in the corners, at all distances, even at the widest aperture. And there lies the problem. Underwater, a flat wall at a distance of 1 meter will have a virtual image that is curved like this dotted red line. This is because in the middle it is at a distance of 1 meter, but 90 degrees to the left and 90 degrees to the right, it will be at infinity. A lens behind a dome port underwater cannot properly focus on the center and the corners of the virtual wall at the same time, because that virtual image is curved. That is what makes the corners blurry. It's like trying to focus on the inside of a sphere. Here you see what that blurriness looks like in an underwater photo. This is the problem of field curvature. What can we do about this? First, let me state that this is mostly a problem with extreme wide-angle lenses. With standard zoom lenses and macro lenses, this field curvature is not much of an issue, because you're only looking at a small part of the curved virtual image. Thus, the curvature of the virtual image becomes more shallow. For extreme wide-angle lenses, there are 3 ways we can fight the blurry corners. The first solution is stopping down your aperture. This will increase your depth of field, making it easier to focus on the entire curved virtual image. The downside of this method is that you will have to increase the ISO to compensate for the loss of light, creating noise. And you would be pushing the lens beyond its optimal optical performance because of the light diffraction that occurs at very small apertures. The second solution is to increase the radius of the dome. This will increase the distance of the virtual image, making it easier to get both center and corner into focus, because as we focus further away, the depth of field increases. This is why I said in the last episode that the bigger the dome radius, the better. It is easier to focus on the inside of a hemisphere the size of a skippy ball than on the inside of a hemisphere the size of a ping pong ball. This is also why you see that many manufacturers produce 9.5-inch domes nowadays. The bigger, the better. But better only in the optical sense. I'm sure I don't have to explain the downside of this strategy. Things get very unwieldy very fast when you try to solve the problem this way. The third and best solution would be to use a lens that does not focus on a flat plane, but on a curved shape that coincides more with the curved shape of the virtual image produced by the dome port. Those lenses do exist. We call them fisheye lenses. Fisheye lenses do not focus on a flat plane. It would be impossible to design such a lens. Think about it. Say you are focusing such a fisheye lens at a right angle on an infinite wall 1 meter away. Where would the corners be focused on? With an angle of 180 degrees from one corner to the opposite corner, the lens would have to be focused on infinity in the corners. As you move forward, you would focus the lens closer and closer in the center, but the corners would have to remain focused on infinity. So the corners would have to stay focused on infinity no matter what you focus on in the center. This is impossible to design, and you wouldn't want a lens like that even if it were possible. Now, while the shape that a fisheye lens focuses on may be curved, it is not identical to the shape of the virtual image produced by the dome. But it's a lot closer than the flat plane of a rectilinear wide-angle lens. Because it's not a perfect match, bigger domes still improve the image quality of a fisheye lens. It would be nice for underwater photographers if the manufacturers of fisheye lenses would tell us how much field curvature their lenses have, but unfortunately they don't. So we just have to try and hope for the best. Now some of you may wonder where I got the 32.5 centimeter distance from the center of curvature to the virtual image of an object at a distance of 1 meter from the center of curvature. A very simple formula allows you to calculate this, but it may be beyond what many of you want to learn. Please indulge me while I demonstrate this for those who want to know. First of all, please note that I will ignore the thickness of the dome port. The optical density of the glass or acrylic dome port is closer to the optical density of water than that of air. If the index of refraction of the dome port was the same as that of water, they would merge into one optical element. We could then simply use the inner radius of the dome and the result would be very accurate. But as the index of refraction of glass or acrylic is higher than that of water, the formula becomes an approximation. So here is the formula. 1 divided by Vd equals 1 divided by 3 times r plus 1 divided by d, where Vd is virtual distance, r is dome radius, and d is the actual distance. Mind you, these distances are measured from the front of the dome, not from the center of curvature. That is why you see the 3r instead of the 4r we saw earlier. So for a dome with a radius of 10 centimeters and an actual distance of 90 centimeters, we get 1 divided by the virtual distance equals 1 divided by 30 plus 1 divided by 90. Note that I have used an actual distance of 90 centimeters because these distances are measured from the front of the dome. So I have to subtract the dome radius of 10 centimeters from 1 meter. So 1 divided by virtual distance equals 0.0444. Turning both sides of the equation upside down gives us the virtual distance is 22.5 centimeters. Add the radius of 10 centimeters, and we get the distance from the center of curvature of about 32.5 centimeters. I think this is a good time to end this second episode on dome ports. To summarize this episode, the water on the outside of the dome port acts as a negative lens, creating a virtual image of your subject that is much closer to your camera than the actual subject. This virtual image is curved. This curving is known as field curvature, and it can be hard for a camera lens to focus on this curved virtual image. Field curvature is especially a problem for extreme rectilinear wide-angle lenses. It is far less of a problem for standard zoom lenses and almost irrelevant for macro lenses. Using smaller apertures reduces the blurriness in the corners caused by field curvature. Increasing the dome radius reduces the blurriness in the corners caused by field curvature. Fisheye lenses deal much better with the field curvature of a dome port than rectilinear lenses do, because fisheye lenses do not focus on a flat plane like rectilinear lenses do. The formula that gives you the approximate distance of the virtual subject to the front of the dome port is 1 divided by Vd equals 1 divided by 3 times r plus 1 divided by d, where Vd is virtual distance, r is the dome radius, and d is the actual distance. Well, that brings us to the end of this episode. I hope you have learned something new from it. Please join me for the next episode, where we will delve deeper into the subject of fisheye lenses. I will show you how you can test the suitability of a fisheye lens for underwater use before actually taking it underwater. If you like what I'm doing here on this channel, please help me out by liking and subscribing. Bye-bye.